in this lecture, we're going to be looking at uniform circular motion, free body diagrams, and Newton's first law. So the textbook reference, if you want to read over the material covered in this lecture, is sections 4.5, 5.1, and 5.2 of your textbook. So first of all, a quick recap of the most important ideas from the last lecture. We saw that everything we have learnt applies to more than one dimension, and it's easiest to split vectors into components and deal with each dimension separately when solving complex problems. We saw the kinematic equations that apply when a body undergoes constant acceleration. And they can be written as v is equal to u plus at, where v is the final speed, u is the initial speed, a is the acceleration, and t is the time over which that we're considering. We've got s is equal to ut plus a half at squared, where s is the displacement, u is the initial velocity, t is the time, and a is the acceleration. And we've got v squared equals u squared plus 2as. We saw that projectile motion is an example of something that has got constant acceleration. So the kinematic equations can be used to describe projectile motion. We saw that the velocity of A relative to B is given by the formula v of A relative to B is equal to the velocity of A minus the velocity of B. So on to new material, uniform circular motion. So a particle undergoes uniform circular motion if it travels around a circle at a constant speed. So the question is, what remains constant during uniform circular motion? And there was a list of things on this form to choose between. We could choose speed, which does remain constant. It tells us that here in the definition. Okay, now velocity. As the particle is going around a circle like this, the velocity is not actually remaining constant because the direction of the velocity is always changing. So even though the speed remains constant, so the magnitude of the velocity remains constant, the direction's changing, so velocity is not constant. The acceleration, that's also a vector, so the acceleration is actually always changing direction with time as well, so that's not constant. Because the acceleration's not constant, the force on the object, which is causing that acceleration, is also not constant, it's always changing direction. And the other thing that we could choose was period, and the period does remain constant. If it's going at a constant speed and it's got a constant radius, then the time it takes to go once around the circle always remains the same. Okay, so when we're considering uniform circular motion, the speed is given by v is equal to 2 pi r over t. So this makes sense as this is the circumference, which, if something's going around a circle, is the total distance it travels, divided by the period, which is the time it takes to go once around. So that's divided by the time. So that makes sense. But now let's consider the direction of the acceleration. So we'll do this more formally later, but we can do this fairly intuitively. So let's draw the velocity at this point. As it's going around in the circle, the velocity is a tangent to the circle. And then at this point, the velocity is a tangent to the circle as well. So let's call this our initial velocity, and this our final velocity. And let's work out the acceleration between the initial velocity and the final velocity. So we know that acceleration, at least the average acceleration, is equal to v final minus v initial over t, and these are vectors and acceleration is a vector. So if we're drawing vectors for this, we've got v final is going that way, and then we're minusing v initial, which is going this way. We're dividing by t, and t is a scalar, so it has no direction. So this is equal to v final, which is this way, and when we subtract off a vector, we add on one which is going in an opposite direction. So we add on this one, and you can see that the acceleration, well, the change in velocity is directed this way. The time doesn't affect the direction, but it will affect the magnitude of this thing. Vf and Vi is going at a constant speed, so they've got the same magnitude. So if we were calculating angles for these exact 2 points, which are kind of 90 degrees with each other, this would be 45 degrees in here. But the important point is if we draw this average acceleration between this point and this point, on the circle, you can see it's pointing towards the center of the circle. So the acceleration always points towards the center of a circle when an object's undergoing circular motion. Okay, so we're going to derive some important equations that we'll need to describe uniform circular motion. So uniform circular motion means that it's moving with a constant speed. And we've also got a constant angular velocity. So let's start by considering a particle which is here at t equals 0. So we'll call this one here theta equals 0. And then in some time t, it moves up to this point here. So if we draw a line there, the angle in here, let's call that theta 1. And at t1, it's at this point here. Now, because this is a circle, the length along here is r, and the length along here is also r, the radius of the circle. Now, the angular speed is given the symbol omega. So this is the lowercase Greek letter omega. And this is equal to the change in angle over the change in time. So if it's starting at an angle 0 at time 0, this is just equal to theta over t. And to get the instantaneous angular speed, we can differentiate theta with respect to t. So for uniform circular motion, this thing is constant. So we can say, well, the total angle it's traveled through then is given by omega times t. Now, what we want to do is come up with some expressions for the speed and the acceleration. So in order to do that, let's write down how the position of our object, which is undergoing circular motion, changes with time. So we can write the displacement as, looking at this point here, if we were to measure its x value, it would be equal to this length here, which you can see is equal to r cos theta 1, and this along the y-axis up here we've got the length r sine theta 1, with this being angle theta 1 here. So if we had some random angle theta, then we can say, well, s, the position, is equal to r cos theta in the I direction plus r sine theta in the j direction. And we know how theta is changing with time because we've just written down this formula here. So this is equal to r cos omega t in the I direction plus r sine omega t in the j direction. And now if we want to get the velocity is the derivative of the position. So we've got v is equal to ds dt. And so differentiating this, we can write this as r omega, and when we differentiate a cos, we end up with a negative sign. The omega came out from here, times sine omega t I, plus when we differentiate this sign, we get an omega out the front, so r omega cos omega t j. So we can work out the speed if we want. The speed is the absolute value of the velocity. So when we do that, we've got a vector, it's in the negative I direction, so it's going back this way, r omega sine omega t, and then in the j direction, up like this, we've got r omega cos omega t. So adding those together head to tail to get the magnitude, this is the square root of r squared omega squared that occurs in both these terms, times cos squared omega t plus sine squared omega t. And so this is, these two things added together are 1, so this is r omega. So the speed is equal to r omega. There's another way that we could derive this as well if we wanted. From circle geometry at school, you possibly remember that arc length S is equal to r theta. So the speed it's going at is how quickly its arc length is changing. So ds dt is equal to the speed, and this is also equal to dr theta dt. Now the radius isn't changing. The radius of the circle it's going around stays the same. So this is r d theta dt, and d theta dt is omega. So this is equal to r omega. So these two are in agreement for the speed of the particle going around the circle. Okay, but let's go on and get the acceleration. So to get the acceleration, we need to differentiate this. And when we do that, we've got here, we pull another omega out the front, so minus r omega squared cos omega t I, plus we pull another omega out the front, and this actually becomes negative because when we differentiate the cos, we get negative sign. So this is minus r omega squared sine omega t j. So this we can write, looking up here, we've got r cos omega t I. So we've got r cos omega t I there, and r sine omega t j, r sine omega t j. So we can actually write this as minus omega squared times s. So this actually tells us that the acceleration is in the opposite direction to the position. So when the position's here, the position's going from the origin to the point the particle's at. So this is the direction up here of the position. The acceleration is back in the opposite direction. So it's back along here. So this formally shows us that the acceleration is towards the center of the circle. Now, if we want to evaluate the magnitude of this, we'll need the magnitude of the acceleration is equal to minus omega squared times the magnitude of s. Well, we don't need our negative sign there. We can make it positive for magnitudes. So to work out the magnitude of s, we've got s up here. We've got r cos omega t plus r sine omega t, and just the same as we did here, but without the omegas, you can see that's going to have a magnitude r, which makes sense because it's going around the circle, so it's always at a distance r from the center. So this is equal to omega squared r. So we can also write this using v is equal to omega r, like we derived here and up here. So we can write this as replacing omega with v on r, v squared over r squared times r, which is equal to v squared over r, which is what's often used for acceleration. So the important point is the acceleration is directed towards the center and given by v squared on r. Okay, so we're now asked to predict what will happen to the speed and period of a bob as the length of the bob decreases. So we looked at this in class. So we need to make the assumption that tension is constant. Now, if we assume that the tension's constant, it means that there's a constant force applied. And as we'll see later, F is equal to ma. So if this is constant, then A is constant. And we've just shown that A is equal to V squared over R. So we're assuming that this is constant. Okay, now if this is constant, it means that the initial speed over the initial radius is equal to the final speed, well, squared over the final radius. And we're trying to work out what will happen to the speed. So we want to know, well, what's going to happen to this speed. So we can write this as initial radius over final radius is equal to initial velocity squared over final velocity squared. So this tells us that as RF decreases, VF also decreases. So a nice thing we can do is if RF equals a half RI, then we can work out what the ratio of the velocities will be. So this would tell us that we had RI over a half RI, which is equal to 2, is equal to VI over VF squared. So this will tell us that VI over VF is equal to root 2. Or we could say, well, VF is equal to the initial velocity over root 2. Now, we're also asked about the period. So we know that period is equal to 2 pi r on v. So this is a bit difficult because it's got an r and a v. It's dependent on both of these things. So we can say, well, t initial over t final is equal to 2 pi r initial over v initial over 2 pi r final over v final. Simplifying this, the 2 pi's cancel out, and we have r initial times v final over r final times v initial. Now we can replace the r initial and r final with vi squared over vf squared. So this is equal to vi squared vf over vf squared vi. These cancel and we get vi over vf. So this tells us if vf decreases, tf decreases. And if the radius was halved, like we did up here, then we can see, well, ti over tf, vi divided by vi on root 2. So this will equal root 2. So tf will equal the initial period divided by root 2. So it decreases by a factor of root 2, the same as the velocity. So we've got a video to show this here. This one was analysed in Tracker to slow it down so that we could actually see what was going on. So here's the track opened in Tracker. You can get an idea of the speed of the ball from the length of the blur. Let's just pause it here and have a look at the speed. So when the string was around about 40 centimeters long, the speed is around about 6.5 meters per second. So you can see the blur is getting a bit shorter, so the ball is slowing down, the speed is getting slower. And around here, it looks like it's got around about half the radius. So at this point, the speed is equal to just over 3.5 meters per second. So before we had 6.5 meters per second, and that divided by root 2 gives us 4.6. So it's going just slightly slower than the original speed divided by root 2. Which isn't surprising as it was losing some additional energy due to friction and other things. So here's an example problem. A woman rides a carnival Ferris wheel at radius 15 meters. So radius is 15 meters, completing 5 turns about its horizontal axis every minute. So 5 turns per minute. So we can use this to work out omega. Omega is equal to the angle it goes through over the time. The time is 1 minute, so that's 60 seconds, and it's doing 5 turns. So that's 5 times 2 pi radians. So this is radians per second. So this is equal to 10 pi over 60 radians per second. And we're given that the Ferris wheel turns at a constant rate. What is, first part, the period of the motion? So the period is the time it takes to complete one complete circle, and it does that 5 times in a minute. So the period is the seconds in a minute divided by the 5 turns. So that's equal to 12 seconds. Every 12 seconds, it completes one complete circle. Part 2, the magnitude and direction of her centripetal acceleration at the highest point. Okay, so the acceleration is given by v squared on r, or we can also write it as omega squared r. So this is probably easier in this case because we've gone ahead and worked out omega at the start. So this is equal to, simplifying this a bit, we can get rid of the factor of 10. So we've got pi on 6 squared times the radius, which is 15, which when we solve it on the calculator, we get 4.1 meters per second per second. Now, this is asking for the magnitude and direction of her centripetal acceleration at the highest point. So at the highest point, she's going like this. So the acceleration is always directed towards the center of the circle. So in this case, it's going to be downwards. So we should include the direction here, downwards. Okay, now part 3 says the magnitude and direction of her centripetal acceleration at the lowest point. So that's here. So we can see when the velocity is this way, then the acceleration is going to be this way. But because she's going at a constant rate, this part's all going to be the same. The actual numbers are going to be the same. So this will be 4.1 meters per second upwards. Now, if you want to practice some extra centripetal motion questions, for Phys 1121, try set 1, questions 11 and 12, or for 1131, try questions 13 and 14. So the next thing we're going to be looking at is free body diagrams. So free body diagrams are really important for solving mechanics problems. So they're a really useful way of picturing all the forces that are acting on a body. So free body diagrams show all the forces that are acting on a body. They show the direction of the forces acting on the body, and they show the relative size of the forces that are acting on a body. So let's have a look at a couple of examples. Let's say that we had a system of weights set up like this. So we're considering these hanging masses in the middle. If we want to draw a free body diagram for these hanging masses, we need to show all the forces that are acting on it. So if this is our hanging mass here, we've got the weight force, which is pulling the hanging mass down. So we can show that downwards, and it's got a magnitude mg. Now the other forces acting on it are the tension from these two strings. So this tension is caused by this hanging mass here. But for the free body diagram on this hanging mass, it doesn't matter that the tension's being caused by this mass. It matters that the tension is acting on these hanging masses. So we've got the tension force acting like this, so we can call this T1, tension 1, and then we've got another tension force which is pulling it up this way, caused by these hanging masses. So we can show that like this, T2. And so that is a free body diagram showing all the forces that are acting on this hanging mass here. So how about the forces acting on the mass on an inclined plane like this one? Well, we've got the weight force pulling it down. Now we've got also got a normal force which is perpendicular to the plane. So this is acting up like this, perpendicular to the plane. Now if there is no frictional force, this mass is going to start to slide down the plane. If it is stationary, then there must be some frictional force pushing it up the plane to counteract the component of the weight force pushing it down the plane. So this is the free body diagram for this mass here. Now Newton's first law we'll be looking at all of Newton's laws. They're really important for describing how the forces that act on bodies. So Newton's first law tells us that an object at rest remains at rest, and an object in a state of constant motion remains in constant motion, unless acted upon by an unbalanced force. So another example problem, a block with a mass of 1 kilogram is at rest on a plane inclined at 30 degrees to the horizontal. What frictional forces act on the block? Okay, so a good way to start this question is by drawing a diagram. So let's draw our inclined plane here. It's inclined at an angle theta is equal to 30 degrees. And here's our block at rest on the plane. Now, since the block is at rest, Newton's first law tells us that there is no net force acting on the block. So we're going to need to use this fact to work out what the frictional force is. Okay, so let's draw a free body diagram for this block. So we've got the weight force, mg, which is pulling it down. We've also got the normal reaction force, which is perpendicular to the plane. So that's going up like this. We'll call that M. And then this weight force is pulling the block down the plane, but the block's not moving. So the frictional force must be pushing it back up the plane. And we know that if we add all these vectors together, so let's add them together head to tail. Here's mg. Here's our normal force, and then here's our frictional force. These must all sum up to give 0. So the frictional force and the normal force are at right angles to each other, as the normal force is perpendicular to the plane and the frictional force is parallel to the plane. Now we can see because the frictional force is parallel to the plane, so it's in this direction along here. And since the angle down here is 30 degrees and this angle here, considering this triangle here, is 90 degrees, this angle in here is 90 minus theta, 90 minus 30 in this case. So this angle in here is 90 minus theta, which means that this angle down here must be theta. So now what we can do is split our weight force up into components perpendicular to and parallel to the plane. Now we're doing this because the friction force is parallel to the plane, the normal force is perpendicular to the plane. So if we split the weight force into components perpendicular and parallel to the plane, then it's easy to add it to the frictional force and the normal force component by component. So we can split this into a component parallel to the plane like that and perpendicular to the plane like this, and using a similar argument with the angles here, this is theta down here. These are at right angles to each other because one's parallel to the plane, one's perpendicular to the plane. This is mg. So we can see parallel to the plane, we've got mg sine theta, and perpendicular to the plane, we've got mg cos theta. Now, using Newton's first law, we could see that there's no forces acting on the block. So this tells us two things. Both of the components must completely sum to 0. So forces parallel to the plane must sum to 0. So the force is parallel to the plane. We've got the frictional force pulling it up, and we've got part of the weight force, this mg sine theta, pulling it down. So we've got that the frictional force must equal mg sine theta, which is what we've been asked to find. So we can now substitute everything in. This is 1 times 9.8 times sine of 30. And solving this, sine of 30 is a half. So this is 4.9 newtons, and this is up the slope. Now the question doesn't ask us to do this, but we can also find the normal force. So the normal force must be equal to the component of the weight force perpendicular to the plane. So this tells us that the normal force must be equal to mg cos theta. While the weight force is pulling it down into the plane, the normal force is pushing it up out of the plane. So these two completely cancel each other out and it doesn't move. This is a fairly challenging problem. So we're told at t1, which is 2 seconds, the acceleration of a particle is in counterclockwise circular motion is 6.00 I plus 4.00 j meters per second. So let's just sketch what this is going to look like. At t1, the acceleration is going to be 6.00 I, and then we've got plus 4.00 j. So we can work out the magnitude of the acceleration using Pythagoras' theorem. So this is 6 squared plus 4 squared, which is equal to the square root of 52. Let's just leave it that way at the moment. So if we consider, here's our circle, we can see the acceleration's up in this direction. We know that the acceleration's always going towards the center of the circle. So at t1, the particle must be somewhere like around here, and it's moving in the counterclockwise direction like this. Now the other thing we can do is we can work out this angle here. Let's call this angle here theta 1. So we can say, well, tan theta 1 is equal to the opposite, which is 4, over the adjacent, which is 6. So solving this, we get theta 1 is equal to 33.7 degrees. So if we sketch this in here, theta 1 is also up here, alternate angles on parallel lines. So that angle in there is theta 1. Now we're told at t2, which is 5 seconds, the particle's acceleration is given by this expression. So we've now got 4I, and then it's minus 6j. So it's going down like that. And so the resultant acceleration is down like this. Now, these numbers have the same magnitude. So the magnitude of the acceleration is still the square root of 52. Let's call this angle in here theta 2. And we can see that tan theta 2 is also equal to 4 over 6. So theta 2 is also equal to 33.7. Now, the acceleration goes towards the center of the circle. So the particle must be up here at t2, and the acceleration's down this way. So we've got this angle in here is theta 2. Now we're asked, what is the radius of the path taken by the particle if t2 minus t1 is less than 1 period? Okay, so we know that t1 is 2 seconds and t2 is 5 seconds. So it takes 3 seconds to go this far around the circle. Now, theta 1 and theta 2 are equal to each other. So hopefully you can see that if it's going from here to here, it's going through 270 degrees, 3/4 of a circle in the 3 seconds. So in 3 seconds, the particle travels around 3/4 of the circle. So to determine this, we needed to know that t2 minus t1 is less than 1 period. Now we know the magnitude of the acceleration, and we also know that the acceleration for circular motion is given by v squared over r, where v is equal to the total distance traveled, which is the circumference, divided by the period. So we can write this as 2 pi r on t squared times 1 on r, which is equal to 4 pi squared. Now that'll be r squared, but we're dividing by an r. So we've just got 1 r left on the top, and we've got a t squared on the bottom. Now this is helpful because we can work out the period. If it travels around 3/4 of the circle in 3 seconds, it's going to travel around 4/4 of the circle in 4 seconds. So t is equal to 4 seconds. So we can now rearrange this and get, well, r is equal to t squared a over 4 pi squared, and these are all things that we know. So we can now substitute in, and we've got t squared is 4 squared times a, which is root 52, over 4 pi squared, and this is equal to 2.92 meters, and I've given that to 3 significant figures. So in this question, a boy rolls a stone in a horizontal circle of radius 1.5 meters and at a height 2 meters above the ground. The string breaks and the stone flies off horizontally and strikes the ground after traveling a horizontal distance of 10 meters. So the range is equal to 10 meters. What is the magnitude of the centripetal acceleration of the stone during the circular motion? Okay, so this question combines circular motion and also projectile motion. So what we'll need to do is kind of work backwards. So the stone is undergoing circular motion, then it flies off with some initial horizontal velocity only. So we know uy is equal to 0. The vertical initial velocity is 0. And it travels a horizontal distance of 10 meters. So we can use this distance to work out the initial horizontal speed if we knew how long it took to get to the ground. So to work out how long it took to get to the ground, we can use the fact that it started 2 meters above the ground to calculate how long it's in the air for. So if we use s is equal to ut plus a half at squared, and considering the vertical components, then we know that sy is minus h. It starts at a height of 2 meters and it drops down to 0 meters. And this is equal to uy, which we've said is 0 because the stone flies off horizontally. So this is 0. And then the acceleration which is acting on it is just gravity. So this is minus a half times 9.8 times t squared, and h, that's minus 2. So I'm just substituting in for that there. Sorry, it's 2.0, it's not 2.00. Okay, so we can solve this to get the time. So this tells us that the time that it's in the air for is equal to 2 times 2 from this half divided by 9.8, and then we need to take the square root to get rid of this squared. So this is equal to 0.639 seconds. Okay, so now we know how long it's in the air for. Now we can get its initial horizontal speed. S is equal to ut plus a half at squared, and we'll put little subscripts x, but there's no horizontal acceleration, so this is 0. And so we can rearrange this and say, well, ux is equal to sx on t, which is equal to the range, which is 10, and now we've got 0.639. So this tells us that the original horizontal velocity is 15.65 meters per second. Okay, so now we know how fast it was traveling around the circle, because that's this horizontal velocity. So now we can use our circular motion equation. A is equal to v squared on r, where v is this velocity that we've just calculated here, to calculate the magnitude of the acceleration. So this is 15.65 squared divided by the radius, which we're told up here is 1.5. And solving this, we've got 160 meters per second, and I've given this to 2 significant figures because the data in the question was given to 2 significant figures. Okay, so in this question, a force F pulls a block up an inclined plane with a constant speed v. Now, we know if it's moving with a constant speed, then Newton's first law tells us that there is no net force acting on the body. So the plane is inclined at an angle of theta to the horizontal. Friction is not negligible. It has a magnitude F friction. So let's draw a diagram, because it's always a good idea to start by drawing a diagram. Here's our inclined plane. Here's our mass. And it's being pulled with a force F up the plane. So if we draw a free body diagram showing all the forces acting on this mass here, we've got the force mg pulling it down. We've got a normal force perpendicular to the plane. We've got the force F pulling it up the plane. Now, if it's moving up the plane, the frictional force has to oppose the movement, so it has to actually be down the plane. We'll learn more about that when we learn more about friction. Okay, so part 1 says draw a free body diagram showing the forces acting on the block. So we've done that there. Part 2 now says write an expression for the component of the weight force acting down the plane. So to do part 2, we're splitting our weight force, which is down, into a component parallel to the plane and perpendicular to the plane. So these are at 90 degrees to each other. Hopefully you can see that that angle in there, which is the same as this angle here, because this is vertically downwards and this one's parallel to the plane. This is vertically downwards, this is parallel to the plane. So considering this triangle here, this here is 90 minus theta, and so this angle down here must be theta degrees, as all of these have to sum up to 180 degrees because it's a triangle. So this tells us that the component of the weight force acting down the plane, that's this one, must be equal to mg sine theta, this side here. So part 3 now says write an expression for the magnitude of F. Okay, so we know that when we're considering the forces parallel to the plane, they must sum to 0 because there's no net force. So forces parallel to the plane sum to 0. So that tells us that, well, the force F is pulling it up the plane. The component of the weight force, this one mg sine theta, is pulling it down the plane, as is the frictional force. So we know mg sine theta plus the frictional force must equal F. And this is just worrying about magnitudes here because these ones are in the opposite direction to these. So this is our expression for the magnitude of F.